Hello again. We are exploring how to represent propositions in type theory, and we made the assumption that propositions are actually the same thing as types. So we're seeing how far we can get with this. So we managed to represent implication, and now let's see what we can do about conjunction. So we ask the same question again. What is a proof of A and B? And it shouldn't be too hard to realize that a proof of A and B is a proof of A and a proof of B, right? And that sounds exactly like a tuple of proofs. So we can represent this using the product combinator from data product, which you type by doing \times. So we make this identification. We say that and is the same as product. And let's see if this works. So the first thing that we would expect to prove is that if I know that A and B holds, then I should know that A holds. Right? But this, of course, is exactly the first projection of the tuple, which is called proj1 in the standard library. So that's almost by construction of what this product is. And here's another example. If I know that A holds, then I should know that A and A holds. So let's see. So I have to prove this. So here we're using that function space is the same as implication again, by the way. And then if I move across this identification, then I have to write a function of this type. So I take an argument, I'm going to call it A. I reload, and I see that I have to produce an A and an A. Well, I can refine this, Control-C, Control-R, and I say that I have to give two things. I'm going to put a bracket around this, because it looks nicer. Okay, and in this goal I have to give an A, but I do have an A, so I give that. And in this goal I have to give an A, but I have an A, so I give that, and I reload. Okay, so we see that this logical fact, the proof of it corresponds to this function which takes an A and duplicates it into two components. Okay, so we could also do conjunction. That's reassuring. Let's see if we can just do true and false. So what is true if we make this identification? Well, it's any type which has an element, right? So the canonical thing to use would be the unit type, which you can find in data unit. And here the type is called top, which you type by doing \top. So we can look at this, and we always have to go hunting a little bit deeper. Data unit base, and in this built-in module here you can see the definition of top. So it's a record called top, it has a constructor called TT, and there are no fields. And remember, to give a record you have to give an instance for all the fields. So here there are no fields, so it's really easy to give an instance for all the fields. Okay, so let's go back. So that's the definition of the unit type. And let's see if we can prove this example. So here we're saying that if you can prove B for any type B, then you can prove true. Okay. So I'm going to introduce a B on the left-hand side as an argument, and now here I have to prove true. But if you remember, there was a constructor for this type, it was called TT. So I can give that, and TT is always of this type. So this says that I'm not going to use the B, I'm just always going to return the constructor. And the thing about records is that they are completely determined by their constructors, so actually Agda can infer that whatever element you give this type, it must be the same as this constructor, because they are the same for all their fields. That is, because they don't have any fields. So actually we can just put an underscore here, which means Agda, you go away and figure it out. And if I load that, we see that that's still fine. And if I were to normalize this, although you have to be a bit careful, so I say x4, and then you have to instantiate what type B I want. So maybe I will use top again, and maybe that's not so good. I'll do top arrow top as my type B, and then here as my little b I can use the identity function. Okay, so now I can normalize this test. So I do Control C, Control N for normalize. I want to normalize the expression test, and we see that it prints TT, even though we gave an underscore, which means figure it out. And Agda did figure it out and return TT for us. Okay, I guess we can leave that in. So that's how we represent things that are definitely true. How do we represent things that are definitely false? Well, that should be a type which doesn't have a proof, right? So that should be an empty type, which you can find in data.empty. So let's go hunting again, and here we see that the empty type is given by a data declaration with no constructors. So there is no way to actually construct anything of this type, right? So for the record, there were no fields, and that meant that it was really easy to give all the fields. But for a data constructor, you have to choose one of the constructors in order to construct something. But if there is nothing to choose from, it's really hard to choose one. So there is no way to construct any elements of this type, right? So we can look at this example, which looks similar to the previous one, but now instead of saying that there's always a way to go from any b to top, here we're saying that there's always a way to go from bottom to any b, right? Okay, so how do we prove it? Well, I can introduce an x on the left, and now I can pattern match on the x. And remember, pattern matching means that we have to deal with all the different cases, but in this case, there are no cases, right? So I do that, and Agda sees that there are no cases and says that, well, this impossible pattern is good enough. And so we've covered all the cases, that is none of the cases, because there are none. Okay, let's stop for now.